All right, so we're getting set to begin the Universal Quick Disconnect blind mate development, testing, and specification. Online with me is Mark Sprenger, a tech lead from Intel, and he has been leading this program for the handmates in the past as in the blind mate currently. And then I'm Jordan Johnson, mechanical engineer at Intel, and have been the lead test engineer on the Universal Quick Disconnect handmates and blind mates for the past couple of years. So Mark, do you want to kick us off?
Sounds great. Okay, so let's jump into the presentation. So what I'll do is we'll be going over really a culmination of a lot of work that started in 2017 internally at first at the Intel Corporation with our liquid cooling working group, and then ultimately we engaged with the real experts in the industry and within the framework of OCP to enable cooling ingredients within a cooling loop. And this presentation primarily we'll be talking about the universal quick disconnects and primarily the blind mate universal quick disconnects, and covering a couple papers that were published to OCP website this year. The white paper, which really goes over the strategy and methodology of the development of the blind mate connector, as well as the testing of the blind mate connector, and the specification, which also was approved this year, which leverages quite a bit, and we'll talk about that in a second, the specification that was approved last year in 2020 and is also available on the website. And all of these papers, white papers and specifications were presented within the working groups within OCP, as well as the OCP Incubation Committee. So I'll talk a little bit about Intel's ecosystem and where we started, and I'll kind of expand that out to some of the strategies and things that we employed to enable the ecosystem. And we took a look at the technology cooling system, which is really the loop that goes from the CDU through a series of tubes, tubing, interfaces, manifolds, interfaces to the manifolds, back into the tubing, and then ultimately to the interface to the IT equipment itself through disconnects, which ultimately are dry break type disconnects that would feed into the internal cooling loop, which would consist of cold plates and another internal loop as well. A lot of work goes into that area with respect to Intel's enabling efforts as well. Not part of this particular ecosystem enabling effort. Within this effort, we looked at the cooling fluid, which really is a big part of the effort, and a lot of effort went into material compatibility and testing of those materials, with primary purpose of simplifying the ecosystem with common materials and common interfaces for that matter, which was one of our initial charters for this liquid cooling group within Intel. In addition to that, we took a hard look at the supply chain, and not just the individual ingredients or the technologies that go into those individual ingredients, but some of the pain points of the supply chain to really look at areas where we could influence or make an impact to really target one of our charters, which is to make these ingredients readily and globally available. In addition to that, we did want to target requirements that are very specific to the liquid cooling industry within the data center. And to that end, also from a simplification standpoint, to not deviate too far off the beaten path in terms of the state-of-the-art technology. So we wanted to align closely to what was currently in the industry and what's been used in the industry for a long time in other areas. So where do we add value to the electronics cooling industry? Well, like I said, we took a hard look at the ecosystem and teamed with our internal global supply chain team to really try to understand the pain points in the process. from the viewpoint of an integrator who's integrating all of these technology components, whether it be cooling loops or IT equipment or cabinets or what have you. Ultimately, a common interface, very much like an electrical plug, has a common interface to a socket, and there's no need to specify a particular supplier. That was the goal with the universal quick disconnects, is to make that interface universal, so that any supplier's plug would fit in any supplier's socket. And this ensures that or simplifies the ecosystem by allowing interchangeability between the suppliers, especially if you look upstream to the or downstream to the integrator. It simplifies their lives in terms of specifying or creating SKUs of the various IT equipment that goes into play. In addition to that, we tried to look at what the timing of this was, and trying to understand the various technologies or advancements in our industry that may occur today, tomorrow, in 5 years from now, and really look at what kind of technologies might come into play within the liquid cooling industry, and how what we do today might play into what tomorrow's reality is. And we focused in on the cooling loop and direct cold plate type cooling systems with these universal connectors. But in fact, we also considered, material compatibilities and how these might play in other technologies as well. Moving into, the various cooling methodologies or advanced cooling systems that might occur. And so, by developing these that are also closely aligned to the current state of the art, we knew that we could develop a solution that is closely related to some currently off-the-shelf designs that may be for other industries, like hydraulics and such, with the flat face type connectors, that would enable, I think, a quicker adoption, as well as a quicker development cycle for these blind mate connectors that are specific to our industry. So then it comes into the actual specification itself and how we develop this. Like I said before, the UQDB, or Universal Quick Disconnect Blind Mate specification, is very closely aligned to our handmade specification in every way that we could, as a matter of fact. So many of the dimensions, especially the diameter dimensions within the internals of what you see here, are the same between the two specifications. This allows for number one, a quick development cycle, as well as try to maintain as much of the tooling as possible from the previous design. Now, there are some nuances with the blind mate connector that don't exist within this handmade connector. For instance, on a handmade connector, you can control very closely the engagement depth between the plug and the socket. For blind mate connectors, of course, you're going to be driven by how closely you can have your panel and panels line up when it's engaged fully in the system. And to that end, there's a number of dimensions that were added to the blind mate connector, keeping our strategy of a minimum set of prescribed dimensions. But things like the panel-to-panel distance, the overall maximum diameters of these individual parts, all come into play in this case, because the system design engineers will have to understand those volumes that are necessary for keep outs and engagement and those types of things. But we did, as you can see, there's not much definition internally on these systems or on these connectors. And so each supplier can continue to differentiate on really what I think is their secret sauce in terms of the internals of this mechanism to ensure a dry break connection, disconnect, as well as to maintain a particular pressure balance or pressure flow drop within the system. And we'll talk about that on the next slide. So the requirements also in this case are very much related to the handmate requirements, because it's targeting, of course, the same system level requirements. And so for pressures and burst pressure, we're at 100 psi for the operating pressure, and 300 psi or 3x the operating pressure for burst pressures. A set of minimum CVs. Now this is a bit different than the handmate, because in this situation the CV values are going to be related to the amount of engagement. So if you fully engaged your valves, you will get 1 CV, and it will change very slightly when it's at a minimum engagement. And so we've specified this at your minimum engagement, which would give you your lowest CV values, is what we determined. And so that's where we specify it here. The flow rating, also similar to what we had in handmate, and the temperatures, operating temperature and shipping temperatures are also the same. And so I'll go ahead and hand this off now to Jordan to talk about the mechanical performance in terms of testing the UQD valves.
Excellent, thanks, Mark. Appreciate it. So looking at this requirement table a little more, I think the key metric here when you're looking at a universal disconnect is its performance, and not just, does supplier A perform well when you use supplier A parts, but does supplier A perform well when you combine it with supplier B? So the focus of this testing is to look at this CV value and to verify that no matter what suppliers are mated with each other, that they meet or exceed that minimum CV value, depending on size. A quick background on what CV is and then how we measure it, and then I'll dive into kind of the testing methodology and setup and test fixturing. CV is simply defined as the flow coefficient, and as you can see on the screen, it's defined as the flow rate of the fluid through the component times the square root of specific gravity over the pressure drop through that component. In this case, in the specification, this is defined with water, and our testing is done with water, so you can safely assume specific gravity is equal to 1, since specific gravity is defined as a density of fluid over density of water. In this case, you rearrange the equation, you get flow is equal to CV square root of pressure drop, and it's pretty straightforward to see that if you can measure flow and pressure drop through the component at different flow rates, you'll be able to calculate what the CV is for that UQDB pair. So with that, getting into the test setup, you can see kind of a simplified version of our test setup here, essentially using a CDU to push fluid past the differential pressure sensor through a certain length of hose that is calculated for uniform flow, and then ultimately through the test fixture and then the UQDBs themselves. Test at multiple flow rates to get that full pressure drop curve and recording the pressure or change in pressure values across the UQDBs at these different flow rates. One other thing I want to highlight here that is different from the handmates. So that setup that you see on the left is essentially the same from handmate to blindmate, but the big difference on the blindmates are those different engagement that is allowed within the blindmates. Like Mark mentioned, they can be fully engaged, they could be unengaged up to 1 millimeter per the spec, they could be radially fully aligned, or they could be radially misaligned up to 1 millimeter. So we want to look at not only nominal, but can we look at the performance at those disengaged and misaligned setups. And so this fixture, there's more detail in the white paper on what this fixture is composed of, but essentially it lets us repeatedly look at those different engagements across all different suppliers as they mix and match them. So then the next thing, we do test kind of supplier A to supplier A and everything, but what I want to call out here is what we're really looking at from Intel's side is, are they truly universal? So does supplier B when mated with supplier A, meet that minimum CV requirement, and so on throughout this matrix where you see those check marks. That's what we really want to look at statistically, confirm that with the amount of samples we run, we have a high confidence interval that they will meet or exceed that minimum requirement. So now to get into kind of more the procedure of the testing. As you can imagine, if you're pushing fluid through that fixture I showed you that changes alignment as well as this length of hose, there's going to be some inherent pressure drop within your system. And so if you don't account for that, then you're not really understanding what the pressure drop through the quick disconnects truly is. So you can see here the green line on the graph there represents the kind of what we call our calibration run or your tear run. Really, it's just the pressure drop through your system. You run the same test recipe, essentially just without any quick disconnects, using a straight flow adapter, and that'll give you the pressure drop of that system. Then later, when you collect your data, you get a pressure drop curve with the universal quick disconnects installed in the test fixture. That will give you that orange line on top, and you simply subtract the calibration run, and the remaining pressure drop is what was brought about by those connectors. So now to give an example, you run through the testing of a quick disconnect pair, you subtract the calibration run in post-processing, and you have this pressure drop curve. And what I was kind of hinting at earlier, you now have this equation. Flow is equal to CV times the square root of the pressure drop. So then you can graph pretty simply the flow versus square root dP, do a simple linear fit, and the added benefit here is you can look at how well this data fits that line to confirm you're getting the data you expected. And then simply the CV is the slope of that line. So we run this testing on all those different configurations, maximum engagement, minimum engagement, radially aligned, misaligned, flow direction, socket to plug, and plug to socket, really looking for that worst case, and then looking and making sure that all of these meet that minimum specification. The next thing, the next question is, so what, right? So they all meet the minimum specification, but as a data center operator, are you still going to be comfortable mixing and matching these universal connectors from different companies? And so what I want to look at now is a worst case that we evaluated with the handmates, and that we're going to continue to do with the blind mates as well. Just as an example, let's say you have a rack with 8 servers in it, and you have extremely good, well-performing universal quick disconnects. Maybe they have a very high CV, right? Because we only specify a minimum. So maybe they have twice the CV that is required as a minimum, and then for 7 of those, and then your 8th rack, both the inlet and the outlet pair, maybe they only meet that minimum CV value, right? So that means that a given flow, your 8th rack would have a higher pressure drop. But if we look at this system, you can assume the pressure for the flow into the rack is one pressure, and the pressure at the outlet from the rack is another pressure, right? So the pressure drop has to be equal across every blade. So the only way that can be true is if the flow actually decreases through that 8th server. So that's kind of the worst case scenario. Let's say you have 7 really great universal quick disconnects that far exceed the specification, and an 8th that just meets the minimum requirement. Are you going to have problems cooling that 8th blade? And so what we did, we built a calculator that essentially iteratively solves this kind of idealized problem of matching the flow rates, the system flow rates, and the sum of those 8, as well as looking at the pressure drop, across all is equal to see what the actual impact on flow is to that last server blade, and then from there, what is the actual impact on cooling temperature. What we found when we performed that calculation is that there really isn't an effect. The pressure drop through the blade is so much higher than the actual UQDB that any change in that UQDB is essentially negligible, and there's no significant impact on the flow through it. It's or the temperature kind of capture, the heat capture. So the takeaway there is, these truly are universal. We're seeing that even with no max CV value specified, as long as they meet that minimum requirement, they will work. As long as they'll work universally, they'll work supplier A to B. There should be no issue diversifying the supply chain and using these kind of standardized connectors from any company. So call to action now, similar to some of the rest in this cold plate group, please review this specification, the white paper. It goes a little more in depth on this methodology, covers what we talked about today, just a little more detail. And then also, again, with getting involved with the ACS cold plate sub-project group, meets monthly. This is the location that all this kind of cold plate innovation and discussion occurs monthly. So with that, we do have, I think, a few minutes for questions, if there's any in the room or online.
Yeah, please, anybody with a question, step up and ask it. We do have a few minutes. Can I ask a question then?
Absolutely.
So it's interesting that you commented that the pressure drop within the server is so great compared to the universal quick disconnects that it kind of gets swamped out, and the variability between them doesn't really have that much impact on the flow. Have you evaluated the different range from device to device, though, internal, to see what the variability of internal pressure losses are, and whether or not they could end up with some kind of a maldistribution situation?
We've taken a look at the maldistribution issue in terms of a particular program that we were working on, and we looked at the differences between the flow rates or pressure drops on a given system versus another system. And indeed, the pressure drop between those systems, the variability is greater than the variability you would see in the QDs. So yes, there is that, and it's a definite concern. And you'll have the variability there also overshadows the variability you would see in a precision defined UQD.
Well, thank you.
Mm-hmm.
Any other questions, please?
Okay, well, if no questions, thank you all for your time. I'll be here, and then if there's any online, we'll be able to respond to those directly. So thank you.